Hi, we meet again. We continue with 4.2 specific heat capacity, or the symbol that we use is small c. Okay, specific heat capacity of a substance is the quantity of heat needed to increase the temperature of a mass of 1 kilogram by 1 degree Celsius. Okay, so that is the definitions of specific heat capacity. Okay, so an object with big specific heat capacity, it can store more heat. So since it can store more heat, so it will heat up slowly, and also it cools down slowly. Okay, so that is the consequences of having a big specific heat capacity. Okay, so it heats up slowly and cools down slowly because it can store more heat, okay, without a very significant change in terms of the temperature. The quantity of heat absorbed or lost from a body is given by the formula Q equals mc theta. Okay, a very familiar formula, I believe, whereby theta is actually our final temperature minus our initial temperature. Maybe I should put a modulus here. Okay, make sure that this number is taken as a positive value. Okay, just to ease your calculation. All right, not compulsory, but just to ease your calculation. All right. So we go to question 12. Applying principle of conservation of energy, heat being absorbed or released from the following cases can be calculated by using. Okay, so if we are using electrical energy, okay, so for electrical energy, I have PT, okay, power multiplied by time. So this PT equals mc theta, right? If we have gravitational potential energy, for example, a ball fall from a building, so we have a height there, right? So here I have mgh, okay, must equals mc theta. If you have kinetic energy, then we have 1 over 2 mv square equals mc theta. Okay, so remember what principle of conservation of energy say. Okay, it simply says that the total amount of energy remain the same. Okay, because energy cannot be destroyed, energy cannot be created, but it can transform, it can change from one form to another. All right, for example, here our electrical energy is being transformed into something else, okay, into heat energy, right? Okay, we move on. Here we are going to use what we have discussed earlier. I have a 700 watt of electric heater used to heat 2 kilograms of water for 10 minutes. Calculate the temperature rise of the water, and you are given the specific heat capacity of water is 4200 joule per kilogram per degree Celsius. Okay, so who supply energy? Okay, it's electrical devices. Okay, so it's electric is supplying energy here. So I have PT, okay, received by the water. So the heat energy that the water will have will be mc theta. Okay, so P is 700. Okay, so I just put it here, 700 watt. And then the time is 10 minutes, but we don't work with minutes. Okay, we always work in second. So the time 10 minutes, so we convert this to second. Okay, so that would be 1 minute we have 60 seconds, right? So minute can be cancelled. So here the time is 600 seconds. Okay, so the time here is 600 seconds equals to m. Do we know our m? Yes, the mass is 2 kilogram. Okay, so 2 kilogram. And do I know my specific heat capacity is given 4200. Okay, so here is 4200. Okay, multiply by theta. What is theta? Okay, theta is the difference between the final temperature and the initial temperature. So in other words, theta is actually the rise, okay, the rise in the temperature. Okay, so calculate the theta. Okay, so if you have done this calculation, you should be able to get that this theta is 50 degree Celsius. Okay, can you follow? So here we are applying the principle of conservation of energy. Electrical energy is transformed into heat energy stored in the water. Alright, so let's move to the next one. Here I have a copper block weighing 2 kilograms. So here I have a mass. Drop from a height. Okay, drop from a height, meaning I have gravitational potential energy. Okay, so what is the notation that we use for gravitational potential energy? Okay, normally I will use this notation, EP. Okay, whereby the height is 20 meter. And we are to find the final temperature of the copper block given that the initial temperature is 28 degrees Celsius. So this is our initial temperature and we are to find what is the final temperature. And then we are also given the specific heat capacity of copper is 400 joule per kilogram per degree Celsius. So this is the value of our C, right? Is 400. Okay, so drop from a height. So I have EP, gravitational potential energy, equals to my heat energy. Okay, so EP would be mgh equals mc theta. So as you can see here, we can cancel our m. Okay, the mass is equal, so we can just cancel this m. So g is 10, h is, what is h? Where is h? Okay, h is 20. Okay, here is my h, right? So h is 20 meter equals to C. Okay, C is 400. Alright, and then this theta is actually final temperature minus initial temperature. Okay, just for the sake of solving this problem, I will just leave it as theta. Okay, so here is theta. So calculate theta. This one you should be able to get 0.5 degree Celsius. That is our theta. Okay, that is the increment in the temperature. But remember that our theta is equal to final temperature minus initial temperature. Okay, so the difference in these two temperature is 0.5. Okay, and then the final temperature is what we want to find out. Initial temperature is 28 degrees Celsius. Right, so solve for final temperature. You should be able to get 28.5 degree Celsius. So that is the final temperature. All right. So try to understand that. Huh? So again, here we are using the principle of conservation of energy. All right. Let's move on to questions number 15. Now I have a bullet traveling. Okay, traveling. So it signals kinetic energy. So for kinetic energy, I'm going to use notation E sub k. Okay, that is my kinetic energy. So we are given the speed. Okay, here is the speed of the bullet, 60 meter per second. The temperature of the bullet rises by 4.5 degrees Celsius. So here is my theta, right? Remember that theta is equals to final temperature minus initial temperature. Okay, but here the rise is 4.5 degrees Celsius. And you are to calculate to find out what is the value of C. Okay, so from the principle of conservation of energy, kinetic energy equals to my Q. Okay, what is the formula to find kinetic energy? 1 over 2 mv square equals mc theta. Alright, so I can cancel m here, correct? Alright, so let us substitute our value into the equation. So I have here 1 over 2, v is 60 square, okay, equals c is what we don't know. We want to find out what is the value of c, and then my theta is 4.5. Alright, then you solve for c. Okay, so this one you should be able to get the answer 400 joule per kilogram per degree Celsius. Okay, you can embed the unit in your calculation. You will be able to get this final unit. Okay, it's joule per kilogram per degree Celsius. Okay, I hope you are still with me. Okay, try to understand how we solve the problem. Okay, let's move to question number 16. Okay, questions on sea breeze and land breeze. Okay, can you see the leaf of this coconut? It is flowing to the left, right? So here I have the sun, so meaning to say this is daytime. Okay, so here is daytime. It happened during daytime. Okay, so down here it happened during nighttime. And I can see here that the leaf of the coconut here is moving to the right. Okay, so the wind is blowing to the right. But for up here during daytime, the wind is blowing to the left. Okay, so what happened during daytime? What causes sea breeze and what causes land breeze? Okay, let's answer the sea breeze first. So during daytime, what happened? Okay, so during daytime, the land and the sea will receive the same amount of energy from the sun. Okay, but the difference is the sea. Okay, the sea, it has a greater specific heat capacity. Okay, so see here, it has greater specific heat capacity compared to the land. Okay, land, it has a lower specific heat capacity. So what does this mean? It simply means that, okay, the sea, it can store more heat energy. Okay, it can store more heat energy, and then the temperature is not significantly increased. But for the land, since it has a low specific heat capacity, so it can store very little heat, okay, in comparison to the sea, all right. Hence, the temperature above here, it will be increased, right? Because it can store less energy, so the temperature will be increased significantly, so the air here would be hotter. Okay, so hot air will go up. All right, this is hot air will go up, and then what happened? Yes, the cool air from the sea, it will move to the land. Okay, so this causes the sea breeze. All right. Okay, do you understand that? So let us write the answer. So during daytime, okay, the land and sea, okay, receive the same amount of energy. Okay, that is point number one. So this energy is from the sun. Okay, point number two, land. Okay, land has a lower sea. So therefore, the temperature or its temperature is higher than the sea. Okay, that's point number two. And then we move on to point number three. The air above the land becomes hotter. And it will flow up. Okay, and then what happens is cooler air from the sea flows toward the land. Okay, so that is point number three. And then we go to the last point. Okay, point number four, the movement of air, okay, causes the wind to blow from the sea. And produces sea breeze. Okay, so we have term for this, right? Whereby hot air going up and then replaced by cool air. Okay, remember this word? Convection. reaction. Okay, perolakan in bahasa Melayu. Alright, try to understand the discussion here. Okay, so during daytime, both the land and the sea will receive the same amount of energy from the sun, but since that the specific heat capacity of the land is smaller, so it will become hotter. Okay, the air above the land will become hotter, so it will goes up. Okay, it will go up, and then the cool air will replace the hot air here, so you will feel that wind is blowing from the sea towards the land. Hence we call this as sea breeze, because the breeze is coming from the sea. Right? So what happened during night time? Okay, so point number one. Okay, so just write the answer first. Okay. Point number two. And then point number three. And then finally, point number four. All right. So what happened during nighttime is both the land and the sea, okay, they are going to release the heat to the atmosphere. Okay, remember that during a daytime, they both receive the same amount of energy from the sun. And then we also know that C, okay, the specific heat capacity for seawater is greater. However, the specific heat capacity for land, okay, is smaller, right? So the seawater, it has higher C, so it has more heat, so it can release more heat compared to land. So what happened? The air above here become hot, all right? So the hot air, it will flows up, okay? And then it will flows up, and then we have convection happening here, and then cool air from the land will move to the sea. Okay, so here I have cool air or cooler air, right? So again, we have convection here. So the movement of the air, this will produce wind to blow from the land towards the sea, all right? Since the wind is blowing from the land, so we call this as land breeze. Okay, you get it? All right. Okay, try to understand the concept behind it. Okay, let's move to question number 17. Now I have 100 grams of hot water at 90 degrees Celsius is mixed with 200 grams of cold water at 30 degrees Celsius. And then assuming that no heat is lost, calculate the final temperature of the mixture. Okay, no big deal. So here, what do I have? Okay, who supply heat. So I'll just put here as heat supply or supplier. Okay, so who supply the heat? That would be the mass 100 gram. Okay, mass 100 grams. And then I have the temperature. That would be the initial temperature would be 90 degree Celsius. And then heat receiver, that will be mass of 200 gram, and then the initial temperature is 30 degree Celsius. All right, so we mix these two together, okay, until they are at uh, equilibrium, okay, thermal equilibrium, meaning to say that the final temperature must be the same. All right, so here I don't know my final temperature. Okay, this one also I don't know my final temperature, but these two final temperature must be the same. All right, so what happened to this temperature? It will decrease, right? And here definitely it will increase. All right, so the heat supply must equal to the heat received. So here I have mc theta equals mc theta. So I can cancel my m. Alright. What about my theta? Can I cancel? Oops. Okay. That is careless mistake. Okay. Is our m the same? No. Okay. We don't have the same value of m, right? So here I will put here ms. Here is mr. Supplier and receiver. How about the C? Can I cancel my C? Okay, here water. Down here is also water. So water must have the same specific heat capacity. So therefore I can cancel my C. Okay, can you follow? Alright, so the mass of the supplier is 100. Okay, so I will just write here 100. And then for this theta, I know that my theta is always equal to the final temperature minus initial temperature. And we would like to take this as a positive value. Alright, so here I do know that my final temperature will decrease. So a smaller number minus a greater number, you will end up with a negative value, right? So I am going to reverse this and just to make it positive, right? So I will write here 90 minus the final temperature. Okay, so that I will have a positive value here, because I do know that my final temperature, it will be lower than 90 degree. Okay, so here the mass here is 200. Okay, and then theta, that will be final temperature minus 30 degree. So why I put it like this? Because I do know that my final temperature would be greater than 30. So a greater number minus a smaller number, I will get positive. That's why I arrange it like this. Alright, so you do your calculation, okay, correctly, you will get your final temperature to be 50 degree Celsius. Okay, so that is our final temperature. So try to understand how we have worked these problems out. So I stop here. We will meet again later on. Okay, so I'll see you again.